This week's clearest signal is that AI is getting better at improving itself, but also better at fooling us about how well it understands what it's doing. In one case, models look humanly cautious on risky decisions until you change the framing and their judgment collapses into boundary-following behavior. In another, more test time sampling stops helping because the draws are too correlated and the vote just amplifies the same mistake. Meanwhile, diffusion language models are starting to learn from their own trajectories instead of external labels. Here's what that means for evaluation, scaling, and self-improvement. Let's explore the first paper, Probing Outcome Level Resemblance and Mechanism Level Alignment in LLM Risk Decisions Evidence from the St. Petersburg Game. This paper studies 28 LLMs on the St. Petersburg Game to separate outcome level resemblance from mechanism level alignment in risk decisions. In the original unbounded game, most models appear human-like by giving finite willingness to pay bids, with median bids of $20 at tau equals 0 and $10 at tau equals 0.7, but mechanism probes expose a different pattern. Under 20-toss truncation, 25 of 28 models at tau equals 0 and 26 of 28 at tau equals 0.7 collapse to the exact computational boundary, $21. And repeated play, endowment, and occupational identity variance often yield conditionally rational or boundary tracking responses rather than human-consistent directional shifts. Human cue prompting and instruction tuning mainly lower bids without reliably repairing the underlying response profile. For example, human cue prompting improves only 23 of 112 mechanism transitions at tau equals 0 and 19 of 112 at tau equals 0.7, while instruction tuning improves 12 of 42 and 8 of 42 transitions, respectively, with most cases unchanged. An EV-first prompt that explicitly asks models to compute expected value does not eliminate the effect. Finite bids still dominate, and 25 of 28 models remain computationally rational on truncation at tau equals 0. The core finding is that apparently cautious LLM behavior in risk tasks can be surface level, so evaluation should test whether decisions remain mechanism consistent under nearby changes in horizon, wealth, and role framing, not just whether the final number looks human-like. Let's explore the second paper, When More Sampling Hurts the Modal Ceiling and Correlation Ceiling of Test Time Scaling. This paper, by Youngyi Bei and Kathleen A. Yerrick, argues that test time sampling in language models has two different ceilings that are often conflated, a correlation ceiling for estimation and a modal ceiling for selection. Reframing repeated decoding as clustered binary sampling, the authors derive the effective sample size NEF equals N 1 plus N minus 1 row, showing that correlated draws saturate at 1, row effective samples, and that the marginal value of the nth sample decays quadratically, so extra sampling quickly becomes redundant. They then separate coverage from selection. Pass at n can keep rising toward what the model can ever reach, but plurality vote or self-consistency converges to the most common answer, with benchmark level accuracy capped at the modal hit rate pi mode. On release logs from Brown et al. Repeated sampling runs, they estimate between problem correlation around 0.4, 0.6, meaning 104 samples per problem are worth only about 2 independent observations for benchmark mean estimation. On Beeching et al., 5-session Llama 3.2.1b, Instruct Math 500 log, 256 attempts per problem, yielded coverage of 0.88, but self-consistency only 0.45, while the median effective answer count was about 13 distinct modes, explaining why more samples sharpened a confident wrong answer rather than improving selection. The practical takeaway is explicit. Estimate row from logs, report NEF alongside N, spend budget on more problems for evaluation, and reduce answer concentration, not raw sample count, when no verifier is available. Let's explore the third paper, DOPST on Policy Self-Distillation for Diffusion Language Models. DOPSD, from National University of Singapore, adapts on-policy self-distillation to diffusion language models by replacing the external privileged reference used in OPSD with a privilege drawn from the model's own denoising trajectory. The student is trained on genuine intermediate decode states, while the same model acting later in the trajectory serves as a teacher that averages predictions over future mass steps and distills them with a token-level generalized Jensen-Shannon objective. This matters because naive OPSD collapses in diffusion settings. On Dream, 7b, Instruct and LLADA, 8b, Instruct, the answer-only OPSD variant barely moves from the base model, and the full solution variant sharply degrades, including a 14 2-point GSM 8K drop on Dream and a 13 2-point drop on LLATA, confirming the paper's claim that instance-specific privileged information becomes a weak PI-free consensus. By contrast, DOPSD is the only method that improves every benchmark in the study, raising Dream 7B, Instruct from 81.41 to 83.04 on GSM 8K, and from 38.97 to 42.2 on Math 500, while also improving out-of-distribution code generation from 52.54 to 56.71 on Human Eval, and from 57.43 to 58.49 on MBPP. On LLATA 8B, Instructed lifts GSM 8K from 71.23 to 72.87, and Math 500 from 31.24 to 36, again transferring to Human Eval and MBPP. Ablations show that a forward KL target, a full future trajectory window, and a mass threshold of 0.5 are the strongest settings. And even without rollout verification, DOPSD still beats the base model, indicating the main gain comes from trajectory-derived, on-policy, privileged supervision, rather than external labels. That's a wrap on today's AI paper highlights. Thanks for watching.